Hey everybody, it's Tom Terrams with the FujiNet project, and I wanted to make a video here showing a preview of the burst mode functionality that I'm working on for the NCIO handler. Burst mode is literally a mode in which you try to do as much data transfer over the serial I/O port as possible. This is absolutely important because CIO, at its very nature, only handles 1 byte at a time for every single time it is called. While this makes device drivers really easy to implement, it does impose some performance bottlenecks, which can be overcome if you understand that you can alter the buffer position and buffer length appropriately to do an entire block's worth of transfer in one CIO call. With FujiNet, we actually have the ability to specify exactly how many bytes we wish to transfer, along with the amounts of bytes expected to be transferred in the command frame. So this makes the implementation of burst mode really simple. Essentially, we just have to say we want, say, 4,000 bytes, and then 4,000 bytes come back. We can do that in one CIO call instead of having 4,000 individual CIO calls. To demonstrate this, we're actually going to go into my Ultimate 1MB setup here, and we're going to turn a couple of things off. PBI BIOS is now disabled here, which means things like the high-speed SIO and everything else is also disabled. And we're going to boot into the FujiNet configurator. We're actually going to take and boot an older version of the handler that does not have burst mode functionality in it. It's my copy of Light Cycles here. We'll go ahead and break out of Light Cycles because we don't want to run that. And we'll have a look what's on the directory on this disk. And we have what is essentially, excuse me, a little network hiccup there. We have three basic programs which demonstrate how to use CIO calls to the end device to load a graphic image. The one that we're interested in is screen 3. And if we look at screen 3, we'll see there's not much actually to this. We have one little machine language routine that does nothing but actually set up the CIO transaction that we set up here below. We have some variables that point down into IOCB channel number 1. We open up a graphic image that is here via the end device at a URL. This is a graphic that is in graphics 9 format already. The server is translating it for us and giving us something that we can load directly into memory. We go ahead and poke the appropriate values into the IOCB after we've opened the file. And since we're using command 7, we're saying get characters. And because we're doing the IOCB directly, we can specify where we want this buffer to wind up, which in this case is pointed to by the location of screen memory. And we can specify how many bytes worth of data that we want to push across. Now in this case, it's 30 pages worth of data, or 7,680 bytes, the length of one graphics 9 display. We then take and then do one call to CIO. And once that's done, we close the file and we just sit there so that we can see the results of what happens. Now, I want you to notice something. When we run this program, you're going to notice that every single time that data gets transferred via SIO, there is a beep. The length of that beep is directly proportional to the number of bytes transferred. But more importantly, in between each of those beeps, there is a pause. This happens because the N handler on this disk only deals with buffers that are 128 bytes at a time. So it transfers a 128 bytes worth of data via SIO into an intermediate buffer and points CIO to it to drain that buffer. CIO then takes and is called approximately 128 times to drain the contents of that buffer. Each of that time, CIO is going into the routine, figuring out what it needs to, what IO operation it needs to accomplish, figuring out the buffer positions, decrementing the buffer length, incrementing the buffer position, and then finally calling our routine to do what needs to be done. All I can say with this is thank goodness CIO uses 0 page when it's actually inside the routine, both in terms of being convenient for the handler to be able to only deal with what it needs to deal with, but also to make it, not too horribly slow. My point being is that you're going to hear a beep, you're going to hear a pause. The pauses are when CIO is literally iterating through those 128 bytes of data and finally moving it to the target buffer. This results in what you're going to see is the data coming across in little bits of a stutter. There we go. I mean, we essentially have a picture here that has been dynamically generated by a server coming across the web, and we're loading it in 128 byte chunks, dealing with each of those chunks one character at a time, putting the results of those characters 1 byte at a time into screen memory. Not the fastest thing in the world. The only thing slower would be is if we were to use get and put in BASIC, which really only works 1 character at. The solution, as I said before, is to essentially take the opportunity that you get by calling into CIO, and since you know, first of all, where your target buffer is as part of the IOCB, that's ICBAL and H, and you know the length of that buffer, which is ICBLL and BLH, you know exactly how long the buffer is and where it needs to go, so you might as well just take that information, pass it directly to FujiNet, and let it do everything in one big whomp. The only complication that we absolutely have to deal with is that we need to leave 1 byte remaining to so that the next call through CIO will transfer that final byte in. This is literally done because CIO decrements the buffer length pointer regardless of whether it's 0 or not, because it's using this as it uses because of how it handles the branch conditions inside of CIO. So we have to have at least 1 byte ready to be transferred, the final byte ready to be transferred. But even taking this into consideration, we can now essentially do this. I'm going to take and hit the reset on the FujiNet. And I'm going to do a cold start. And now I'm going to load the latest copy of the nhandler from my file server. As is implied, this version of the nhandler has burst mode read. We'll go ahead and boot it. And I just realized I didn't put the other disk in so I could load the program. So apologies. Let me do this again. I will take and pause so you don't have to go through this again, and we'll come back here like camera magic. And now with the right disks in the right slots, apologies for that, we can now go ahead and load screen 3 again. And again, same program, nothing has changed, but we are now using the burst mode that's in the new in handler. The only thing that has changed is the auto run sys, which now has a burst mode routine in it. And the reason I wanted to do this without high speed on is literally so that you can hear the long beep as it transfers 7K worth of data in one shot. Cool, huh? Let's do that again. Voila. And to finish this demonstration, I'm actually going to go into the Ultimate 1MB setup routine here with the BIOS. And we're going to turn on high speed. High speed SIO enabled for all devices so that the end device is covered. We're going to boot the result. Right now we are running at HSIO divisor number 0, which is 125 kilobits per second. Before we were running at standard SIO speed, which is 19.2 kilobits per second. And again, the same program, but this time running at full HSIO speed. There you go. Let's see that again. Don't blink. And again. Again, it's loading 7,680 bytes in one shot. There we go. So I'm going to go ahead and end it here, but wanted you guys to see this. I still have to implement write support. I still have to fix the end of file condition. But this here basically proves that the routine I just wrote will work just fine and will drastically improve in performance. So until next time, guys, have fun.